Yes, so hello everybody. I'm Oswald Barral. I also come from Finland, but from the University of Helsinki. So I hope you can hear me well. So I'll present this work we've been doing about using physiological measures in order to infer affective responses of the users. In this case, we are trying to predict whether users find certain content humorous or not. So that's a paper, it's a Tokai paper that was published in the last issue of 2017. So, well, the main idea of this study that is presented in this paper is basically we get users to read comic strips that are fetched in real time from the web, and we measure their physiological responses using lightweight physiological sensors, and we train machine learning models in order to infer whether they found a given comic strip funny or not funny. So it's pretty simple. So there is several motivations behind this work. So one of the motivations that we are carrying work in this field of implicit interaction. So we're trying to find ways to improve the communication channels between users and machines that do not require additional effort and interaction costs from the user. And the specific field where we're trying to develop this is implicit tagging. So basically, with the increasing amount of information available, it's getting harder and harder to collect like metadata that is to describe the content and so on. So physiological signals have proven to be one possible alternative. In this specific case, we use physiological signals to try to infer automatically whether users find something funny or not funny. And there is several applications of this specific study. So one would be this implicit tagging, but also other applications include affective recommender systems where recommendations are based on the affective responses of the users, embodied virtual agents that will be able to better understand the affective state of the user, and finally even game design, for instance. So I know some of you in the audience might already be wondering, but hey, why aren't you just using webcams, right, or camera video? We know that nowadays affective expressions are pretty extracting affective expressions from the user's faces is pretty accurate and works pretty well. And it's not the aim of this paper to go against that, but rather to show alternatives, or even to demonstrate whether we can use it in combination with effective other effective measures such as facial expressions, as we know that there is also some drawbacks from using a camera. For instance, we might have some privacy concerns associated with it. We have the problem that we need the person to be in front of the camera to have a clean streaming of their face. There is computational cost and so on associated. So the paper tries to investigate physiological signals as an alternative. So the main contributions of the paper is that we show that fusing or using different signals in combinations improve the predictive performance of our models. We also try to be rigorous and look at each of the different signals in order to see which one contributes better to the models, at which point in time we are able to extract from the signals the most discriminative differences, and so on. So we use this type of white box approach. And finally, we do benchmark with camera-based systems. Okay, so overall, the experiment, we ran an experiment, pretty straightforward, with 25 participants. So we designed this experiment, even though it was happening in our lab, we designed it in realistic, we call it in a realistic environment, and that's from the two perspectives. So on one hand, we have no control over the stimulus that the participant are consuming. So that were jokes that were fetched in real time from the web. So the participants were just instructed to go to a very common humorous website and just browse comics as they felt. And on the other side, it's also in a realistic environment from the sensor's point of view. So we tried to collect physiological measurements from keeping the wearable sensors in mind. So we still have high quality amplifier to measure those signals, but we try to disregard any sensor that requires huge, let's say, cumbersome setups. So we recorded skin conductance with a couple of sensors on the skin, on the fingers. We recorded the cardiovascular activity with ECG, so it's 3 sensors around the chest. And then we recorded electroencephalography, EEG. But in this case, we just use one channel attached to the brain, because other type of standard EEG measurements are pretty much more cumbersome, that involve like 32 or 64 electrodes on the brain. And basically we asked participants for each comic strip that they were reading, just to indicate whether they found it funny or they didn't find it funny. And that they did for about 45 minutes, up to 1 hour, and they were rewarded with a movie ticket. So it's the experiment where participants were the most happy to take part in that I have ever conducted. So yeah, we designed this predictive setup. So we had 3 of the participants, of the 25 participants, that sensors were misplaced, and then we had some problems with the recording, so we had to disregard for the analysis. But for the remaining 22 valid participants, we split them in 2. So the first half, 11 participants, we used those to play around a little bit with the data, try to figure out what are the best feature engineering methodologies we can use, which are the best predictive models, best performing, etc., etc. And once we have define our prediction pipeline, we use those remaining 11 participants, which were blinded during all that process, to just validate our models. And we designed this 2-class prediction setup, so we try to predict from the physiology whether something is funny or not funny. And we try to also look at the differences between what happens when we train models using participants' own data. So for each participant, I train a model using their own data, or which we call within participant models, or what happens when we are trying to build models from other people's data, right? So I take everybody else in my data set in order to train a model for a unseen participant. We use random forest as the prediction algorithm, and area under the RAG curve as the performance measure. And one quick note, I'm not sure how well you can see that, the resolution. It's just one quick note about what we did with the feature engineering. So one of the issues we had, or the challenges we had here, because the stimulus was non-controlled, so we had no control over the stimulus, so we get different lengths of comic strip, different times that participants spend longer or shorter time in each of these stimulus. So the approach we went for is we divided the trials into fixed-term 4-second windows. And so we had this initial 4-second window, the initial window, the middle 4-second windows, and the 4 seconds at the end of the trial. And in addition, we had this, what we call these special windows, which it turned out to be pretty important for our models. And basically, we defined this window, which is spans from 2 seconds before the end of the trial up to 5 seconds afterwards. And initially, we defined that window because we know that skin conductance responses, especially, they have some delay, and they can take up skin conductance can take up to 5 seconds or even 7 seconds to show its peak after the response to a visual stimulus. Okay, so briefly, I don't expect you to understand in detail these figures. There is more details on the analysis and results in the paper. I'll try to just highlight the main points that I think are interesting takeaways for the Kai community. So on the left, I'm sorry, I think the resolution is not the best. But on the left side, we have the across participant models. So these are the models that we trained using, for each participant that we predicted, we trained the models using the rest of participants. And on the right side, we get the models that were within participants, so we trained them using the participants' own data. And the red, so each dot represents the performance of one participant, and the red box plot represents all physiological signals in combination. The green box plot represents the skin conductance, using skin conductance levels alone to predict the humerus responses. Blue represents the electroencephalographic sensor on the brain, and the purple represents the heart rate, the ECG based predictions. So the first takeaway or main result is that we can see we have somehow this type of trend in both cases, in the sense that we get the best performing in both type of models using all the signals in combination. And then when looking at the different signals separately, we get that maybe ECG based models are not, or the ones that perform the worst. And we get a bit comparable results from the skin conductance alone and the EEG sensor alone. And one interesting finding from regarding this latter point is the fact that when we look at the within participants models, we can see that actually using just that one sensor EEG on the brain we reach pretty high predictor performance, and it's also interesting this fact that it is pretty consistent across participants as compared to, for example, skin conductance responses based models. Yes, so again, there's a bunch of numbers and features names. It's not the aim of this slide for you to really grasp everything in this table. But so basically this table represents the ranked feature on the best performing models, which were all physiological signals in combination. And the main point I wanna show about this table is that for all of the different physiological signals, the best performing features were extracted from this window that we call the special window, or the end window, meaning that all of the most important physiological differences were found in the later stages of the trial, which somehow proves the point that the punchline comes at the end in most of the cases. And another interesting insight, maybe for those of you that are a bit more into physiological measures, is the fact that we had this just very simple one signal EEG sensor on the brain, and surprisingly, or we didn't expect that, we get the most ranked, highest rank features on this gamma activity and the amount of change on the gamma activity. And we know that gamma activity usually is able or is known to capture like muscle noise or noise that comes from muscles or even like ambient noise and stuff like that. So we did run some correlative analysis and so on to try to see where this gamma activity came from. And we don't have conclusive results, so we can't say that, okay, this comes from your brain or comes from the muscle necks, for example. But still, it's pretty interesting that we are able to get that high prediction performance just using one sensor on the brain, whether that comes as a proxy for measuring some type of muscle activity or actually it comes from the brain. Okay, so briefly, I'll comment on the results we got when training models based on facial video expressions and also trying to combine both physiology and camera-based models. So as expected, video-based predictions perform better than the physiological predictions. It is true also that here we are missing a couple of participants because we didn't have clean facial recordings from them. They moved away from the field of vision. So that also evidences one of the possible problems that we get when we use this type of camera-based solutions. So again, left side, it's the across participant prediction, right side within participant prediction. Red box plot is using all physiological signals alone. The green box plot represents the video-based alone, and the blue combination of video and physiology. So it's interesting to see that in the across participant models, we are able to improve for the worst performance, mainly in the video-based case, when we include the physiological sensors to the model, so that will be the blue box plot, we are able to somehow correct a little bit for those, so that's pretty interesting. But on the within participant case, so when we use the participants' own data to train these models, we can see that using their own facial expressions to predict whether they found something funny or not, it performs already so good that it is hardly of any benefit to add physiological signals to the models if we have the chance to record camera-based facial expressions. So just to recap, as a summary of what this paper is, I hope that was not too many results in a short presentation, but you can get more details on the analysis and results in the journal paper. So one important takeaway from this study is that we showed that in this case it was beneficial to use several simple physiological sensors in combination to achieve the highest performances in predicting humor appraisal. And another strength of the paper is that we are able to identify for each of these signals separately where, at which point in time, and what are the type of changes that are reflecting the humor appraisal in each of these signals were located. So for skin conductance, we found that integration and change in the later stages of the trial were the most discriminative. For the EG, we have this special amount, so basically the amount of change in the gamma activity from that one channel in the back of the head. And for ECG in general, there was not very good results. And from the main takeaway from the camera-based, or one of the main takeaways from the camera-based benchmark, is that we still, especially in the across participants models, we get the highest performance when combining physiology with cameras. So we get added value by using physiological signals, even in the cases that we are able to record camera-based signals. And yeah, but on the other side, if our system design allows for within models, so we don't have, for example, computational cost problems and so on. It might be that we don't benefit that much from the physiological input. Thank you very much. I'll now take a couple of questions.
We have time for one question.
Hi, Tico Bayagas from HP Labs. I was wondering how physical movement might impact the physiological signals. Like, what was the condition where people were reading the comic strips? Were they sitting and still, or?
Yeah, so of course that's one. Thank you for the very good question. So that's one thing that we have to be very careful when doing this type of physiology-based studies, and it's also about how we report our results and what we claim, right? So, for example, we have these signals we found in the brain sensor, which could be that it comes from, I don't know, for example, like muscle activity or facial muscle activity, even though that it is reflected on that signal, right? So, in similar way. It could be that, so for example, the skin conductance, we measured it on the hand that was not on the mouse. So the participants were actually looking at the screen, sitting, and using a mouse on the right hand, but they had the skin conductance sensor on the left hand. So in that sense, it is unlikely that let's say, movement from the left hand could explain the results, but again, that's one of the main challenges when we try to make these more realistic approaches using this type of physiological sensors is to what extent we are limiting the user movements and the user natural behavior in order to get the best outputs of our models, right? And in this case, we went for this approach of trying to relax as much as possible the control on the user. But again, of course, that might involve some issues in that regard, yes. Thanks.
Okay, unfortunately, we have no more time for questions, but